Okay, so here we're going to take a look at the squeeze theorem for sequences. Similar to when we had the squeeze theorem for functions, right? The idea is this, right? We want to be able to set up a three-part inequality here, right? So in this case, we're talking about sequences. So we have three sequences, right? And we want to set up an inequality that holds not necessarily for all n starting from 1, but at some point, right, then the inequality holds true, right? There's a number that after this particular number, let's say 3 or 4, right, after 3, right, then this inequality holds for all numbers greater than 3, right? Maybe it starts at 1, but it's not necessarily always the case. All right, and the idea here is that these bookend sequences, this a sub n and this c sub n, that they both not only converge, but converge to the same value, in this case L. If I can establish that fact, then what the squeeze theorem tells me is that, well, if it's true that b sub n is less than, the limit of b sub n is less than or equal to L, but also bigger than or equal to L, well, there's only one option for b sub n to be, and that is L. Right? Now, graphically, what that means, if we think of our sequences here, we have 1, 2, 3, etc. All right, so let's say that, all right, this is L. All right, and let's say let's switch up numbers here. Let's say my b sub n is in this color, and then it does something like this, right? Where, oops. Sometimes it's here, sometimes it's here. Right, it kind of has this oscillating behavior here, right? But it's all tending towards that value L, right? And you want to prove that's the case, right? Well, the idea here is that you had something like, let's say a sub n, maybe that one is, right, it's above, right? It does a very particular value here. And then b sub n is maybe approaching it from below. Here, 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 here. All right, but together they're kind of, and you see, right, squeezing it so that we could see that they're both going to be, both a sub n and c sub n are approaching, excuse me, it should be c sub n, are approaching this value of L, right? And that means that the b sub n will also approach that value L. All right, now this is particularly helpful, especially it tends with our trig functions, the sine and the cosine. Like, for example, let's say that I wanted to find whether the sequence 2n minus sine of n over n for n greater than or equal to 1 converges or diverges. And if it does converge, to find the value that it converges to. Right, whenever I see something like this, whether it's a sequence or just a general function and we're asked to find a limit, right, that isn't a straightforward one, right, then the squeeze theorem provides an indirect alternate method to find that, right? And I like to start with the sine function, right? I usually say, right, the sine of n is negative sine of n is always between 1 and negative 1. Right? Now this is true for sine of n and negative sine of n. Right? If you think of the sine function, right, it looks something like this. What that negative does, it kind of switches it flips it across the x-axis, right? But the bounds still hold, right? The max is still 1, the minimum is still negative 1. All right, so whether that's sine n or negative sine n, this inequality holds. And then from there, I kind of try to build what the sequence looks like, right? I'll add 2n to both sides. All right, when dealing with inequalities, you always do want to be careful here, right? Adding any number, whether it's positive or negative, as long as it's the same number across the inequality, doesn't change the inequality, right? The only thing that's going to change it is if you divide or multiply by a negative. So we do have to be mindful of that case, right? Now, the next part would be, well, let me divide by n. But here, since we're dealing with sequences, right, n is always a positive integer. So I don't have to worry about that changing the inequalities, so they remain in the same orientation that we see here. All right, so I've set up my three-part inequality here. All right, so the next step would be, well, let me look at the endpoints, right? The limit as n goes to infinity of 2n minus 1 over n, right? And we see here as n grows very large, the leading terms take over. So this is going to be 2. All right, and then on the other end, the limit as n goes to infinity of 2n plus 1 over n. Again, that plus 1 not contributing to our limit as n gets really, really large, right? What's taking over are these leading terms here. And this one is also 2. All right, so far what we've had is, this is the setup here, right? The limit as n goes to infinity. So we have established this so far, right? Evaluated the n endpoints, and when something is both less than or equal to 2 or bigger than or equal to 2, well, it must be 2, right? And by the squeeze theorem, we could say, by the squeeze theorem, we could say that the limit as n goes to infinity of 2n minus sine n over n is equal to 2. And that's how we apply the squeeze theorem.